Welcome to this session where I will talk about the use of heuristic-based algorithms to select viewpoints and estimate the 3D position of objects. I am Sandro Magalhães and I am a researcher at INESCTEC in the Tribe Laboratory and a PhD candidate at Faculty of Engineering of the University of Porto. INESCTEC is a research institute with headquarters in Porto that aims to foment technology and science. Actually, INESCTEC is wading into 5 different technological areas, and this research is closely developed under the Tech for Agri-Food area. Inside the Tech for Agri-Food, we have the Tribe Laboratory that born into 2014, and it was born recognizing the Portuguese agro-food industry and the strategic research agenda for robotics in Europe. Portugal has a diverse agricultural area, mainly divided into small crops with different kinds of cultivars. In these areas, the use of heavy and large machinery is most of the time challenging and expensive once the country contributes with small crops with a moderate production of food from each crop. So, in the laboratory, we are challenged to deploy robotics and IoT for precision agriculture and forestry. Here we aim to design and prototype small-size agricultural machinery and update the currently used machinery with IoT sensors and actuators towards precision agriculture. Our roadmap aims to sequentially cover all the agricultural topics in the medium term and contribute to the science with application-specific solutions. So currently we are challenging into these 4 areas in the scope of agricultural tasks and some more in the scope of robotics for forestry and IoT for the same purposes. We are mainly driven by the real prototype suitable for being essayed into real conditions in agricultural field partners such as Quinta do Seixo from Sagrap Company. Here we can see 3 different kinds of modular robots designed for spraying, this and this one, for seeding and for vegetal cover maintenance. That is the case of this robot. We have at the back side a seeder, and in the front side we have a cutting tool to keeping the cover vegetation cover. And we are also prototyping some cost-effective IoT devices and sensors towards precision agriculture, suitable for using by human operators or by intelligent machinery. This is our team, and the work that fomented this topic is mainly focused on manipulation and grasping challenges. So, however, more structured than open field scenarios, operating in tomato greenhouses has still some challenges. Into these environments, the use of RGB-D cameras is still conditioned by natural radiation perturbations, and the sensors may lose the sense of depth. The literature is approaching this problem through different kinds of strategies, most of them based on deep learning models. This is the case of Midas algorithm that estimates the depth of each pixel. But these are complex algorithms that require further calibration and many data to refine the models. So here we are challenging to deploy a solution that allows to infer and estimate the position of the fruits into the 3D task space using monocular cameras. For that, we are challenging to deploy strangulation and statistic-based algorithms that allow to do that kind of estimation. So in this solution, we deployed the BVE that claims to use a 9-dance strategy for object detection and positioning into the 3D task space. This algorithm is mostly based on heuristic-based solution for this estimation and focused on using monocular sensors such as RGB-D cameras. So now we'll start by exploring and stating the best viewpoint estimator that we call the BVE. So we'll start with some intuition. Here we have a camera that is observing a fruit, so with a circular shape that is the most similar fruit to a tomato. And for this observation, we are focusing on the orthogonality principle. So If we have an observation of the fruit, we should have an error in this, so in the y and z axis in this case, and a bigger error in the x axis. So we want to minimize this observation, increasing the information about this axis, and then try to effectively estimate the position of the fruit. So assuming the principle of the orthogonality, you should assume if we move toward an orthogonal position to this error, we should minimize and get just this part of the error, the observation error. For that, we'll try to minimize the intersection of multiple covariance matrices that should correspond to the observation error covariance matrix. For that, we will define two different kind of cost functions that will allow to explore solutions to minimize this intersection of covariances. The first one is based on the logarithm of the dispersion of the resulting covariance matrix, and the second loss function we are trying to minimize the maximum absolute eigenvalue of the resulting covariance matrix. And both of these cost functions are subject to some restrictions that try to represent the reality of our system. Here you can see some working example, a simulation based on MATLAB for visualization. So we have a first view of the fruit that is in this place. So we are approximating this observation by these covariance ellipsoids, and then try optimizing the previous algorithm. We conclude that this should be the best position to observe and extract more information about the fruit, considering some restrictions such as this plane. So the sensor, the camera should never intersect and overlap, so cross this wall. And these two solutions are not sufficient, and we find a third position where you can observe these fruits. So we can see that at each iteration, the resulting covariance ellipsoid is reducing. So to test our algorithm, we are also considering some restrictions. The first one, we want to assure that our sensor is also inside the working space of the manipulator. We also want that our sensor is outside of the fruit, so we are just estimating the center position of the fruit, and we don't have the perception of its size. So we are trying to characterize numerically and geometrically this size. And then we are trying to assure in this third restriction that the sensor, the camera, is always looking towards the fruit, and that the fruit is at a reasonable distance to the sensor. And finally, we define that if we detect fruits, such as we saw in the context topic, at greenhouses we have the plants align horizontally, and we don't want to that our sensor and manipulator cross this plant's area, avoiding to damage the fruits and the plants. So in the first case, we are approximating both the working volume of the manipulator as well as the volume of the fruit by two spheres. And here we want to assure that our sensor is always inside of the manipulator, the working volume of the manipulator, and in this second case, we want to assure that our sensor is always outside outside the volume, so the space occupied by the fruits. Then we want to assure that our sensor is always looking toward the fruit, and we want that our fruit fits inside the horizontal field of view of the camera, so we don't have that our camera is too close to the fruit, that the fruit gets outside of the camera, as well as we don't want that our camera is too far off this fruit that barely can see the fruit. And finally, we want that our camera never crosses or never goes to this position. So once we detect a fruit, we are considering that I have a plane aligned to these fruits, and we give a distance to the size, so to the top view of the volume of the plant, area of the plant. It is represented by this D, and we want to assure that our camera never crosses to this space. We say our algorithm we will append to the BVE an extended Kalman filter that will allow to iteratively refine the position of the fruit into small steps. In this case, we will consider small steps of 20 centimeters, and we try to iteratively refine the position of the fruit to get the most close to the real position of the fruit. So for this, we designed some experiments. Here we can see some experiments of the BVE without the extended Kalman filter, using instead the monovisual 3D filter. That is an algorithm based on histogram filters that allow to iteratively estimate the positions of the fruit. So here we are using the BVE to estimate the next best pose to place the sensor, and then you use the monovisual 3D filter to exclude from the discretized space the poses that do not contain the position of our fruit. This was a previous work published in Robotic that you are free to consult and to read. Now, considering the BVE, we design a set of 10 experiments divided into two groups of 5. In the first group, we are considering the dispersion-based cost function, and in the second group, we are considering the objective of minimizing the maximum absolute eigenvalue of the covariance. So here in the first experiment, we are just considering that our sensor should be at a distance of about 1 meter to the fruit. Then we add the restriction that our sensor should be inside of the working area of the manipulator, and then we exclude this restriction and add the size of the fruit and the orientation of the camera towards the fruit. In the fourth experiment, we add that the manipulator should never cross the plane occupied by the trees. And finally, in the fifth experiment, we are also considering the kinematics of a manipulator. In this case, we are considering the kinematics of the robotic manipulator H manipulator. So the camera should always respect the possible positions of this manipulator and should also be valid inside of this scope. So now we can observe some results. Here we are comparing just the results from the experiment 2 and 7 that are considering that our sensor should be at 1 meter to the fruit and should be also inside of the working space of the manipulator. And then here we are considering a system with the full restrictions, respecting also the kinematics position for the manipulator to observe the fruits. Of course, that when you consider less restrictions, our solution works better. And once you increase our restrictions, we have less accuracy and a higher error. Here we can conclude that the use of the dispersion-based algorithm has slightly better results with a slightly better lower error. However, the results are very competitive, mainly when we have more restrictions. Then we try to assess the capability of our algorithm, the BVE, together with the extended Kalman filter to recover with two bigger initial estimation errors. So we consider it initial deviation estimations to the real position of the fruit between 0 and 50 centimeters, and we conclude that the use of the dispersion-based algorithm is slightly better than trying to minimize the maximum eigenvalue of the covariance matrix. But when we have more restrictions, the results are very competitive, so the restrictions are promoting some limitations to our algorithm. Finally, we have another aim that intends to move our sensors toward the fruit while it is estimating its position. For that, we appended to the cost function a function that allowed to increase the penalty according with increasing of the iterations and using for that the distance from the sensor to the fruit. And they conclude that it's very reasonable to use both of these approaches. So we are approximating our sensor towards the fruit while we are also estimating the position of the fruit during this path. So this is an approachable solution that can have very nice results. So to conclude, we designed the BVE, that is a covariance minimization algorithm that try to optimize viewpoints that increase observation information about the object. We appended this BV with the extended Kalman filter and was capable to detect the fruit with a precision till 3 centimeters. This is an algorithm that is data independent, differently of what happens into deep learning based or machine learning solutions, and is an heuristic based solution. For the future steps, we pretend to assay our solution into laboratory and real conditions, and we also intend to extend our solution to trying to evaluate the effectiveness of other detection algorithms such as segmentation and try to observe if we can have better results. Finally, we want to assay the effectiveness of our algorithm for performing tasks such as monitoring or harvesting. Thank you for your attention.